It should have.
Now, on Google, now is there an app that I should download? I didn't download anything for Google Meet.
I don't think you need to download anything. If you do it through Google, it's okay. You don't need
Okay,
to.
let's go.
Yeah, but you can see you can see.
Yeah.
So people are
Okay.
entering. So people are
Except that
entering
I
now.
can't see you. To see you guys, I need to go back here. Okay.
Yeah, most probably when you will be presenting, you will not see us. That is a problem. Or you have to have two screens. In one screen, you can put it, the presentation. In another screen, you can do it. But this is technically a bit complicated issue. For someone who doesn't use Google Drive, I think it will not be working.
Right.
But it's okay. That's
Well,
okay.
I'll do what I can, and I'll leave a few minutes for questions.
Yeah, usually we'll start around. It's
Well,
okay.
I'll do what I can, and I'll leave a few
According
minutes
to the,
for questions.
I think 2 minutes left. Yeah, usually, and then we will
Okay.
start. And Edgar told me that you have another. You have to go.
I know, I know. I was able to tell them that I'm going to be a little late,
Yeah,
but I'll try to.
but you can talk here since something around 50 minutes, and then we can
Yeah.
discuss if anybody has some questions, and then so in 1 hour we can finish it. So you'll not be late in that case.
Okay.
So just maybe in another 2 minutes we can start. Okay.
Okay.
So let me check out one thing.
Oi, professor. Desculpa aí que estou numa correria danada aqui.
Aqui também. É o mal dos tempos.
Vai ser. Mas, bom, a gente vai conseguindo ir para frente.
A gente faz o que pode.
Professor Milton speaks very good Portuguese. I came to know from Edgar. So,
okay. Well, I grew up in Brazil, so.
So you have no problem speaking in English then. do you prefer to speak in Portuguese or in English?
Oh, I make a mess of both languages. Don't worry.
Oh, so you can mix.
I can switch to Spanish and make it even a worse mess.
Okay, so if there is any question, so I can mention that, okay, you can speak in Portuguese. The questions can come in Portuguese. There is no problem.
Sure.
We don't need to translate. Okay.
É que assim, em realidade, quando você me fez a consulta, a gente tinha a expectativa que ia entrar um número maior de participantes de outros países. No final, terminou com que maioritariamente o que temos são alunos do programa e de outras universidades aqui do Brasil. Então, se o senhor quiser treinar aí o português, fique à vontade.
Olha, na verdade, fica meio complicado em português, porque muita da terminologia técnica, aí no Brasil também se usa a terminologia inglesa, gap ou coisa assim.
And you must have lost practice also, I think. I don't know. Language is a bit of dynamic thing, no?
So I don't know if at one point during the meeting you think people are complaining that they can't understand me.
No,
just tell me and I'll switch to Portuguese.
Okay, I think it's time. We should start now.
Okay.
People are still entering. I think people will continue to enter for another 5 or 6 minutes, but we can start. I think it's already 3:30 local time.
Now, are you going to introduce, or should I just introduce myself?
No. We'll make an introduction, and then you can also introduce yourself. But I will invite Udi Miller to give you
Okay.
collaborator. So, okay. So, good afternoon, everybody. let's continue our program of MT2. And it's a great honor to have with us Professor Milton Torikachvili, I think I pronounced it correctly, of San Diego State University. And he will talk about high pressure studies on novel superconducting and magnetic compounds. Professor Milton is one of our collaborators of Professor Yuri Miller, who is our colleague here in Department of Physics of UFA, University Federal of Amazonas. And so I would like to invite Professor Yuri Miller to introduce Professor Milton to the audience. I think it will be nice and more personal. Okay. So Yuri Miller, please.
Bom, boa tarde para todos. O professor Milton é professor do Departamento de Física da Universidade Estadual de San Diego, Califórnia, Estados Unidos. Até o momento, tem publicado mais de 230 artigos, com um fator de impacto de 39 e mais de 7.000 citações no ResearchGate. Área de pesquisa física experimental, física da matéria condensada e novos materiais supercondutores e magnéticos. Então, professor Milton, é um grande prazer para mim apresentá-lo aqui para nossos alunos e colegas que vão a participar conosco em sua palestra. Com você.
Okay, so Professor Milton, so now the stage is yours.
Okay, now I'm on my own.
Yeah. So you can present the same way we did.
Yeah. All right, folks. Thank you, Yuri, for the very nice introduction. Thank you all for this very nice invitation. And too bad we can't meet in person, but let's do what we can. Unfortunately, I'm not too familiar with Google Meet, so we couldn't quite make it work. So I have my PowerPoint presentation here. I'll do what I can to convey the message. And if at any point you prefer that I switch to Portuguese, just one of you let me know and I could switch to Portuguese. It's not that it's going to be much better, because one problem of trying to speak more than one language is that you can make a mess in all of them. Well, I didn't quite know where I was going or the shape of your department. And I've been invited to give talks in places like this, where I have people who know a lot about condensed matter with people who don't know very little about condensed matter and know a lot more about nuclear or some other things. So I thought of, in this presentation, to tell you a little bit about a technique that is very, very powerful. But it's also technically somewhat difficult to implement. It's the technique of carrying out measurements under extreme conditions of pressure. And that has been a passion of mine for the longest time, since I was in graduate school. And I was fortunate enough to learn enough about it that within the last, a little bit as a postdoc and much more in the last 15 years, setting up a high pressure facility where I am now at San Diego State University. So what I thought on this talk is to use about half of the talk to tell you about the technique and some really important findings in the technique. And then for the other half of the talk, I'll tell you a little bit about 4 of the problems that I've been studying over the last few years. Now, are you all seeing me change slides here?
Change the slide, yes. It's okay.
Okay. So I'll start with a 5-minute crash course on condensed matter physics and superconductivity. Okay, it's really a 5-minute. It's just to remind people who don't deal with this every day what this is about. Then I'll move to pressure and pressure techniques, and then I'll move to these 4 systems. And of course, I can't show them very much detail, or certainly I'm going to be skate through the theory, but I just want to show how important, how pressure measurement or measurements under pressure are so important to address important physics in the system. So there is a comedian in the U.S. He had a very active career some 20 or 30 years ago, and he was a little bit of a joker. He said, "Why pay so much time, so much money, and spend so much time at the university, for example, to learn Spanish? You know, if you ever need to learn Spanish, just come, buy me a cup of coffee, spend 5 minutes with me, and I'll show you, I'll tell you a few expressions that you may need, like ¿Dónde está la biblioteca? Or Me llamo Yuri." So this is the 5-minute college degree that I'm going to give you in condensed matter physics and superconductivity. Condensed matter physics and superconductivity and a lot of all the electronic phenomena, they are based on those outermost electrons in those ions. Those are the active ones. There's a very simple model to build upon, and that's the free electron gas model. Just think of a metal or something that is not a metal, an insulator, as a box in which you show some, in which you throw some electrons in. Okay, but now we need to remember the electrons are fermions. Now, are you seeing my cursor here?
Yes, you can see.
Oh, okay. Now, electrons are fermions, so not when you throw them in a box, not all of them can have the same energy. You first populate the low energy states, and as you throw more and more, you start populating the higher energy states. Okay, but here's a situation. If you try to throw energy into the system, those electrons at the bottom, the lowest energy, are not likely to take that energy if that energy is going to take them only up to an energy state that is already occupied. So basically, only those electrons very close to the top energy state are the ones that will be active. They can absorb or give out energy, because by absorbing energy, they can move on to an empty state. Okay. Now, given that the energy is equal to the square of the momentum divided by 2 times the mass, in K space, or the energy has this parabolic shape. The energy has this parabolic shape. So if there is no lattice, that Fermi surface, okay, is going to be spherical. But of course, if you start thinking of this electron gas not as a free electron gas anymore, but an electron gas that you put in a metal, so there is going to be a lattice, then the shape is not going to be perfectly spherical anymore. This is an example of what it is for copper, still relatively simple. If you're going to use to check the Fermi surface for a complex compound, it can be something really complex, and frankly, there's people who make a living trying to understand how this Fermi surface works in more complex materials. Okay. So now the electronic and magnetic properties, they are determined by the interaction between the charge carriers and the lattice. Okay, and of course, sometimes the lattice or the lattice points, there are ions in there that will have a magnetic moment. Then, of course, those magnetic moments are going to interact with the electron cloud. They're going to interact with each other. They're going to interact with the lattice, and a whole bunch of phenomena can have. Sometimes at the Fermi level, you can have an energy gap formation. Some energy or some K values are not allowed, or some energy levels are not allowed. Okay, and that means the formation of a gap. You are all familiar with a case in which there is a gap of the whole Fermi surface, and that when your material becomes an insulator or a semiconductor. Of course, even when you have that total gapping, you may have thermal activation. And when the thermal activation is efficient, we call it a semiconductor. When it's not, we call it an insulator. Now, for superconductivity, you need pairing. Okay, and the pairing of electron charge or hole charge can come from a different number of sources. Traditionally, from the BCS theory, we thought of the electron-phonon interaction or the deformation potential. But now with high-temperature superconductivity and with heavy fermion superconductors, people started thinking about the more exotic mechanisms because just the deformation potential was not given enough. As far as more basic stuff, there's long-range magnetic order. There's direct and indirect exchange between the ions so that they decide to line up in one way or another over an extended distance. There's super exchange, there's double exchange, there's different forms that will yield long-range magnetic order. And there's also structural transformations in which the density or the electron density will somehow interact with the lattice and somehow drive this structural transformations. I like this picture here about this electron-phonon interaction or the deformation potential. I remember as a student I had a difficult time understanding how electrons could pair to yield superconductivity because electrons like to repel each other, right? Well, but in a lattice, you can see this one electron traveling here to the right, and it sort of brings the positive charges, the positive ion cores close to them. Okay, so there's another electron traveling nearby. It will respond to that Coulomb attraction from the positive ion cores moving that direction, and somehow that will yield enough energy to keep those electron pairs bound. Of course, it doesn't take that much energy to break that pair. That's why superconductivity typically happens only at significantly low temperatures. Now, there are more exotic forms of pairing. For example, paramagnons or resonance valence bonds, and there's a whole bunch of other possibilities of pairing that still there's a good number of very smart theorists and experimentalists trying to address. Okay, so why is pressure, how can pressure help us solve some of these problems? Well, we can think that on atoms, individual atoms, when they are very separated from each other, like forming a gas, each one of those atoms will have those energy states very well defined. But in a solid, okay, basically because of the electrostatic interaction between the electron cloud and the ion cores, when you start bringing them close together to this A naught here or sigma naught, I don't know what this is. Basically, what used to be a very well-defined energy state for an atom, now it's spread into an energy band. Okay, here's a case for sodium, where the sodium, I think it is sodium, I'm not sure, not important, but for example, this 3s state, when the separation is large, is the energy state of the 3s in sodium. But when you bring them together in a solid, now you have a band of energy. Okay. So what pressure does in essence is to compress a lattice. But as it compresses a lattice, it can make changes to the Fermi surface. So if there are magnetic interactions, either direct exchange, indirect exchange, now since those ion cores are slightly closer together, so there's going to be change in the magnetic interactions. Also, sometimes, particularly when you look at the rare earth elements, some of them, the valence is somewhat unstable. So by applying pressure, you may be changing the valence slightly. The beautiful thing about pressure is that you can compress the lattice without the introduction of disorder. Okay, unless there's a change in the structural, the crystallographic structure, but you can do that change without, most of the time, without disorder. Sometimes what's called a chemical pressure is you accomplish that shrinkage of the lattice or the pressure not by a hydrostatic pressure, but by substitution. For example, when you substitute a small ion for a much larger ion with the same chemical characteristics, so chemically the substitution works, and that small ion will create this artificial chemical pressure. That's very important, and many important results have been found that way. However, when you do that, you are introducing disorder, which you don't introduce when you're just measuring purely with pressure. Okay. Now, pressure is a thermodynamic parameter, it's an intensive thermodynamic parameter. You can use to fine-tune the density of states without introducing disorder. You can fine-tune exchange interactions. You can promote, suppress, enhance phase transformations, and a bunch of other things. Let me show you a few remarkable examples, phenomenal examples from relatively recent stories, or recent history, last 5 years. For example, superconductivity in this mixture of hydrogen 2 sulfur, hydrogen 3 sulfur, that's the stuff that smells bad. But superconductivity was found at 203 Kelvin under this enormous pressure of 155 gigapascal. This is like 1,000, no, it's 1,550,000 atmospheric pressures. Okay, it's a pressure comparable to only something very close to the core of the Earth. Part of the reason it took so long to get to this pressure is that these experiments are technically extremely difficult to carry out. You may think, well, is it that great that we have a superconductivity at 203 Kelvin at these enormous pressures? How can we use something practical with it? Well, the idea is not to use this result for a practical purpose, but I think the main point is to know that it's possible to have superconductivity at 203 Kelvin, okay, even under pressure, because if superconductivity is possible at those pressures, maybe we can find ways of having superconductivity at these high temperatures without those enormous pressures. Actually, this started in 2016, I think. Then a couple of years later, 250 Kelvin superconductivity at 170 gigapascal in lanthanum hydrogen 10. And more recently, within the last year, superconductivity in this mixture of carbon, sulfur, and hydrogen at 288 Kelvin. Of course, at a higher pressure here, 267 gigapascal. Okay. So basically, they make carbon sulfide. They grind it, loading the pressure cell with a lot of hydrogen, and under pressure, this mixture forms the samples are so small that it's even difficult to determine what is the crystal structure. But there we go, and I'll show you in a minute that these things are superconducting. There's the history also of how high temperature superconductivity was discovered in the copper oxides in the mid-80s. Okay, and I'll show you a little bit about it. Before the 80s, one good example for how important pressure was the gold phase transition in samarium sulfide. See, samarium sulfide, when you fabricate it, oh, it's an ugly gray thing, it's semiconducting, looks like dirt. But when you apply a relatively small pressure, 6.5 kilobar, okay, that's basically 6,000 and some atmospheres of pressure, that ugly looking sample becomes gold color. Okay, and of course, reflecting that it became a metal. Okay. Also, iron. Iron is known for being toxic to superconductivity. Many elements were not discovered to be superconducting until they are purified enough to get rid of all the iron in them. Okay, but then iron itself becomes superconducting at this pressure of 200,000 atmospheres. Let me skip some of this. Let me go directly to the most important result by Snyder and collaborators in 2020. And that superconductivity on that mixture of copper, sulfur, and hydrogen at 287 Kelvin. Okay, that's what? That's like 15 degrees centigrade. It's something that we can get in our refrigerator. Don't even need to put in the freezer. So what you have here in this picture on the left, on the right, is the resistance versus temperature. So you see that in a field of 0 Tesla, okay, here's the superconducting transition. I don't know where they pick up the 287. It's probably right at the middle of the transition of the resistance from the normal state to the zero resistance state. Here it's normalized by the resistance at 290, so that's why over here you're reading 1. Okay. Of course, the sample is so small, these experiments are so technically so difficult. There's always the suspicion. How do you know that it's not only a very small amount of the sample that has zero resistance? How do you know this is the whole sample being a bulk superconductor? Well, this is sort of confirmed over here where you measure the AC susceptibility, which is more of a measurement of the volume than what the resistance is. The resistance, if you have just a percolation path that is superconducting, you would get zero resistance. But here you see that there's a very large change from the normal state to the superconducting state, confirming that this is the volume that is becoming superconductor. But also, as we increase the field, go to 1 Tesla, 3 Tesla, 6, 9, you start driving this transition to low temperatures, which is typical of what happens to superconductors. Okay, I told you a little bit about samarium sulfide before. On this plot on the left, we have the normalized reflectivity versus pressure. So you see at the low pressure, the normalized reflectivity is very small. Okay, the thing is not conducting. Okay, but as you apply pressure, the reflectivity keeps growing. Okay, and it becomes, you reach 80% at a pressure of 6 kilobars. Okay, you may ask, well, how do you know? Why do you call this the gold phase? Well, there's one type of pressure cell where you have a diamond window. So you can see through that as soon as the pressure reaches 6 kilobar, the sample becomes gold colored. Okay. You may notice sometimes you switch to kilobar to gigapascal. Okay, that's a little problem with the field. Of course, gigapascal is the international system, but kilobar, it's still used a lot. Bar is used a lot in measurement of atmospheric pressure. It used to be part of the CGS system, but there's no, no, no biggie. Basically, 10 kilobars is equivalent to 1 gigapascal. And I told you guys a little bit about iron before, right? Iron that is supposed to be so toxic to superconductivity. Under a pressure here of 22 gigapascal or 220 kilobar, okay, it becomes superconducting. The resistance starts dropping at 2 Kelvin and eventually gets to zero a little below 1 Kelvin. Oh, and it's important to mention, we talked about chemical substitution before. See, in 1986, people manufactured lanthanum, barium, copper oxide, which had a record high superconducting transition temperature of 38 Kelvin. But then this man, Paul Chu, who was a pressure specialist, realized, well, lanthanum and yttrium are chemically identical or almost identical, but yttrium is much smaller. So what will happen if I substitute yttrium for lanthanum? So he did, and the superconducting transition temperature started going up, just as he did by applying pure pressure. And eventually he reached this composition, yttrium, barium 2, copper 3, oxygen 7, that became superconducting 90 Kelvin and really started a second revolution on superconductivity. So let me tell you a little bit about pressure cells. I'll speed up here, but I want to give you a flavor for what you can do with pressure cells, okay? The simplest pressure cell that is very good because it gives you really a hydrostatic environment is just a helium gas cell, okay? But here's the problem. The maximum pressure is only somewhere around a 1 gigapascal or 10 kilobar, okay? It's very useful for a few things, but the pressure is very small. Then there's the piston cylinder cell, the type that we use in my lab. You can go up to 2.5 gigapascal. They are good. They're somewhat easy to operate. There's good thermal stability for the sample. The sample volume is very large, so you can do very large things in it. Then there's the Bridgman cell that you see when you go from the piston cylinder cell to the Bridgman cell. You're losing a factor of, 10 or 15 in volume. Your sample becomes very small, but you can get to 7 gigapascal. But when you go to a diamond anvil cell, you can go up to 250 gigapascal, okay? But of course, the volume of the sample is incredibly small. The sample is so small that you can't really pick it with a pair of tweezers. You're just managing, everything has to be managed in a microscope. This is what a piston cylinder cell looks like. It looks pretty much like the master cylinder in a car brake system, okay? Except that it's made out with very hard materials, and it has provision for passing wires to the belly of the beast where the pressure is going to be a maximum, okay? So this number 6 here is what's called a feed-through. So you feed wires through it, and you seal them very well with a hard epoxy. And this is what the tip looks like when you have the wires coming out and a sample attached to it, okay? Then you get that sample, and you put in this Teflon cup, number 7, which is filled with a pressure transmitting medium, like a brake fluid. Then you put it inside of a hole inside of the cell, and with pistons on both sides and lock screws, you take this to a hydraulic press, apply pressure, lock the pressure in, and go do your measurements of resistivity. So this is what the feed-through looks like. And if you look here at the backside, we have a manganese coil and a piece of lead, okay, a 1 centimeter a lead wire, and you use those as manometers, okay, because both the manganese the resistance changes with pressure, and the superconducting transition of lead also changes with pressure. So you measure those, and from that you infer what is the pressure inside of your cell. Okay, and here is the sample. Just to give you an idea, this distance here is about 4 or 5 millimeters. This is about 2 or 3. So all this work to put leads and attach the sample, all this work has to be done in a microscope. And still, this cell is much, much bigger than the diamond anvil cells that I want to show now. Probably this is the best drawing that I can show you here for how the diamond anvil cell works. So you basically prepared 2 diamonds with flat cullet. A cullet is, the flat part. It's usually the pointy part of the diamond, right? The top here is the table, and this is the cullet. But now you flatten the cullet. Okay, and the typical dimension of the cullet is about 500 microns or half a millimeter. Okay. Now, this is what happens. If you just push those 2 diamonds against each other, they will break very, very easily. So the way you do it, you put a metal gasket about a 300 micron, 0.3 millimeters in between the cullets, okay? Then of course, the diamonds, they have to be in a structure like this. This is a beryllium copper structure to hold it. Okay, so they should be lined up with each other. So now you pre-stress, you indent the metal gasket. In this case, is a stainless steel. You indent it, and since diamond is so much harder than steel, the steel is going to acquire the format of the diamond. Okay, then you open it up, drill a very small hole in that metal gasket, and that's going to be your pressure vessel. That's where you're going to put your sample and put your pressure transmitting medium, okay, and then apply the force, lock the force in, and now, for measurements of magnetization, this is relatively simple. For a measure of resistivity, this is much more complicated because somehow you need to have wires attached to your sample, and those wires need to come out, so they will go to your electronics. And they'll go to your electronics so you can measure the resistivity. This should give you an appreciation of how difficult it was for these guys here to collect this data. Okay, I'm going to skip this. This is for more technical about how to measure the pressure, failure mode, so on and so forth. Now, when you work with pressure, very frequently you will get asked the question, how high in pressure can your cell go? And I just love this cartoon from Calvin and Hobbes. I think in Portuguese they are Haroldo, and I forget the tiger's name. So Calvin is this very small kid, and he's traveling with a family on a road trip. And over a bridge, he sees that there's this sign, low limit 10 tons. He's a smart kid, very curious, so he asks the father, how do they know what's the load limit on bridges? And the father, who's a smart aleck, he's trying to be a funny guy, he says, well, they drive bigger and bigger trucks until the bridge breaks. Once the bridge breaks, they know, hey, this is the limit. Okay, so of course the mother, who's trying to educate the kid, is very mad with the father for giving the kid weird ideas. But in a way, that's how a lot of the pressure cell development happened over the last 50 years. Okay, so Let me tell you now a little bit about my experience in 4 systems in which we use pressure to address important issues. First one, lanthanum bismuth, and it's a material with topological properties. This work was done in collaboration with Fazal Tafti from Boston College, and he grew the single crystals. The first thing that we noticed that was really weird is it didn't matter how good the crystals were or bad or how banged up they were, the resistance at 0 magnetic field was very, very small. Okay. But also when you apply a magnetic field of 9 Tesla, the magnetoresistance was huge. You see here on this plot on the right at 2 Kelvin, that the resistance increases by 6 orders of magnitude, okay, at ambient pressure. So we perform a few experiments in pressure, and this is what we notice. As we start applying pressure from 0 to 5 gigapascal, this magnetoresistance starts dropping very, very quickly, okay, like at like at 3 gigapascal, it dropped by 3 to 4 orders of magnitude. And even more important, once the pressure got a little over 3 gigapascal, the material became superconducting. Okay, once you got to 11 gigapascal, there was a crystallographic transformation from FCC to tetragonal. Okay, so this is obviously worth investigating. Okay. A little primer, a very summarized primer about topological materials. There's a drastic change in symmetry at the interface between the bulk and the surface, okay? And that leads to the appearance of some really exotic electronic states at the surface. This non-trivial topology, it doesn't exclude, for example, the presence of gapless edge states, therefore leading to a more conducting behavior. The band structure of the bulk is typical of insulators, okay, with a gap, so on and so forth. However, that gap can be crossed by these topologically protected states. In these topological protected states, the spin and the momentum are locked, okay? And due to time reversal symmetry and Kramer's degeneracy, there's always pairs of these locked states. And they have opposite momenta and spin. So this is what happened because they come in pairs. There's the potential for scattering is much lower because by scattering, they would have to gain energy, but then they couldn't go to another state because the other state is already occupied. So that leads to a suppression of backscattering, and the electrical resistance is very small. The scattering is very small. Of course, there's a great potential for spintronics and quantum computing because, of the obvious reasons where you can change things a lot between the surface and the bulk. Okay. Oh yeah, as far as quantum computing, and might as well put this cartoon here to entertain you a little bit with the issue of quantum computing that everybody around the world is worried about. So this is the boss here. And this is the working bee, one of you or me, the scientist. So the boss, of course, wants results. He comes and asks, how's your quantum computer prototype coming along? The worker says, great. The project exists in a simultaneous state of being both totally successful and not even started. Okay, that's obviously an issue of superposition in quantum mechanics. Then the boss, of course, who doesn't know much about quantum mechanics, asks, can I observe it? Well, that's a tricky question, right? We all know what observation does, Heisenberg uncertainty principle and all. Okay, so we saw in the previous plots that the pressure would lower the magnetoresistance. And here are plots of the resistance in 0 and 9 Tesla at no pressure up to 2.4 gigapascal. And you see that actually the magnetoresistance drops a little as the pressure increases. So what I want you to get from this is that obviously magnetic field is breaking up somehow that that protection of those exotic states. But also more important than that, what pressure is doing is not really increasing the resistance in field, but increasing the resistance in zero field. Okay, you see that at 2.4 gigapascal, that resistance at very temperatures is much higher than the resistance at low pressures. Okay, see, the resistance at low pressure is very small because those states, topological states, are very protected. But if pressure starts breaking up that protection, okay, you see that the resistance increases quite a bit. Okay, I'm going to skip the rest here because it gets too technical. I can switch to the other three systems that I told you pressure can be very useful in elucidating what's going on. So the next one that I want to talk about is cerium cadmium 3 phosphorus 3. Very interesting material. These are single crystals, and you see the metallic behavior here with a current parallel to the AB plane or current parallel to the C plane, to the C direction. Okay. So they are metallic behavior. There's some data. If one could blow up here, you'd see there's some anomaly here at 125 Kelvin, and that's due to a small structural transition. You can see here that the resistance starts increasing a little bit below 5 Kelvin and then start to drop at 1 Kelvin. And that's due to a formation of an antiferromagnetic order a little below 1 Kelvin. Okay, I think they call it here at 0.42 Kelvin. Now, see, cerium is an interesting material because its valence can be anywhere between 3 and 4. And when it's 4, it's completely ionized. But when it's between 3 and 4, what happens, that 4f orbital overlaps, it can hybridize quite a bit with the s orbitals from the Fermi surface. Okay, and that hybridization sometimes mandate what the behavior is. That behavior is described very well by Doniak. And Doniak created, you'll see this in the literature, the Doniak diagram. It came out from the early 70s or late 60s, where he basically carries out a calculation of the binding energy when you have a Kondo interaction or RKKY interaction. So in this case, the RKKY interaction, okay, that's the Rudman-Kittel-Kasuya-Yoshida, is the one for long-range magnetic order. You see that prevails here at this very low temperature, and the material orders antiferromagnetically at 0.4, 0.5 Kelvin. So that's when that binding energy is the largest. That's opposed to the lowest energy of the system. So the material forms as RKKY. But as you increase the temperature, the Kondo behavior starts mandating. Okay, so that's when there's hybridization of the 4f state from cerium with the conduction electrons, and there's scattering, and you have this Kondo state is a ground state that is competing with long-range magnetic order. So let me show you briefly what pressure does to the system. So for zero pressure, okay, you have basically the same behavior that you're seeing here. But as you apply pressure, okay, probably what's happening is you are making the valence more and more towards 3, but you are also forcing the hybridization. You're probably you're moving up here to the right of this intersection point between conda and RKKY, and you see that the resistance starts increasing as you apply pressure. Okay, so there's a lot more to be done in the system, and this is something that we're involved with. Over here, we stopped at basically 2 gigapascal, but we want to start monitoring what happens to the magnetic susceptibility as we keep increasing the pressure. Okay, the third example that I wanted to show is an example that I was involved with, in which there's a formation of a charge density wave. So a charge density wave is an effect in which you start with a well-behaved Fermi surface, but then at a certain temperature, part of the Fermi surface is gapped. Okay, and what happened to those electrons? Well, those groups of electrons, it could be holes as well, they form a density wave. Okay, it can be seen in X-ray. It's very difficult to see it. It's somewhat difficult to see with resistivity too, but this is one example in which we were able to see. So you see this black curve here, the one at the top, is the electrical resistance or resistivity versus temperature. Okay, it comes linearly from ambient temperature, and then there's a little bump here, a little above 200 Kelvin. And that's when you start gapping part of the Fermi surface. Therefore, you have less electronic charge to carry out the energy. So the resistance goes up a little bit. So now what happens when you start increasing the pressure and you go from zero pressure to 2.12 kilobar or 2 gigapascal? Well, what happens is you start driving that formation, that gapping of the Fermi surface to lower temperatures. Okay, and if you plot this as a function of temperature, you'll see that somewhere close to a little over twice this pressure, close to 50 kilobar, the charge density wave could be completely suppressed. There are systems where by suppressing the charge density wave, sometimes there's enough charge there, and if there's enough interaction, the system can become superconducting. Okay. If you extrapolate the normal resistance and see the difference between the real resistance and the extrapolated below the charge density wave formation, you'll see this area under the curve here, where you see that difference plotted against the reduced charge density wave temperature. Then that area under the curve is going to be proportional to the amount of the surface, Fermi surface that is being gapped. Okay, and again, if you extrapolate, you'll see that the suppression will take place somewhere between 50 and 60 gigapascal. I'm sorry, kilobar. And the last thing that I want to show is this one system, uranium nickel 0.5 antimony 2. Very interesting system. It orders antiferromagnetically at 161 Kelvin. Okay, this is the magnetization, or I'm sorry, the magnetic susceptibility versus temperature. So there's these two very strong features here at 161 Kelvin. But if you blow up this images here, you'll see these two very small features that are sort of puzzling. They're centered near 40 and 80 Kelvin. And this is puzzling me to this day. Okay, let me show, I'm going to skip a lot through this just to show you the important thing. If you measure the heat capacity versus temperature, Okay, there's going to be a huge feature here at 161 due to the formation of the antiferromagnetism. And that makes sense, right? You go from a much ordered state, antiferromagnetic below the transition, to a much disordered spin state above that. Okay, so you lose a lot of entropy in the process, and that shows in the heat capacity. But if you look at over here at 40 and 80 Kelvin, there's no indication of that feature. And that's still puzzling to this day, okay? Look, if you look at the thermal expansion as a function of temperature, again, you see features here at 161. And you do see features at 40 and 80 Kelvin. And those features still don't show up in the heat capacity. That's very, very strange. Okay. If you look at the Seebeck coefficient as a function of temperature, okay, there's a large feature here at the onset of the antiferromagnetism. And then there's just two huge features at 40 and 80. And still, they don't appear in the heat capacity. So let me skip and show you what happens in the measurements of resistivity under pressure. Over here at the stop panel, we have the resistivity normalized to 300 Kelvin versus temperature. Okay, these plots are shifted for clarity. So you see that at zero pressure, ambient pressure, you can see the features here at 40 and 80 in the resistance. But as you apply pressure, those features disappear. And that's true both when you are measuring along the plane or perpendicular to the plane. Okay. Very, very puzzling. So this is a problem that we still want to pursue. Okay. So to summarize, I think what I wanted to say to this group in Manaus is that pressure is a very powerful experimental tool in condensed matter physics. Okay, it's not going to solve our energy problem to find out a superconductor that works under enormous pressure and room temperature, but it's going to tell you, maybe it'll give us some hints of what we can do to understand better what happens under pressure, and maybe we'll have an idea for creating better superconductors. Pressure is particularly useful in fine-tuning the phase transitions. And very important, lattice compression can be accomplished without disorder, which is more typical of substitutional studies. As far as what I'm interested in the future, I want to study some exotic superconductors, like the ones with topological behavior or non-centrosymmetric samples. I want to find a way of making more reliable measurements of resistivity and magnetization in diamond anvil cells. And it would be very important also to develop measurements of thermoelectric potential and Hall effect under pressure. Okay, so I'll stop here, and I hope I can switch to seeing you all, and I'll be glad to answer any questions. You can ask me the questions in Portuguese, English, or Cuban.
Okay, thank you so much, Professor Milton. That's great. So you can stop there. Yeah, now we can see. Yeah. So, hello. Now, thank you very much, Professor Milton, for a nice talk. You give us a nice panorama of high temperature, superconductivity under high temperature. We have a small group here who works with high temperature experimental group, but they are they're not working directly with superconductivity, but it must be very interesting. I don't know if they are present here, but so I will keep the audience open for any question. Alguém tem alguma pergunta? Anybody has any question?
I would like to ask a question on the last part of the presentation, where you show Well, first, good afternoon from Manaus, and thank you very much for your talk. I am Anshula, a faculty here at UFM. And I have a question on the last part, which you told now, that there is a jump in the specific heat or the heat capacity. So I would like to know, is it a second order phase transition, or we don't yet know if it is, or whether it is a superconductor?
Oh, okay. Now, uranium, nickel, antimony 2 is not superconducting. Okay. No, it shows antiferromagnetism at the 160. But when you monitor all the other measurements, resistivity, Seebeck coefficient, thermal expansion, they're just two small features at 40 and 85 or something like that. And for example, for the Seebeck, the effect is enormous. So it's really surprising that it doesn't show up in heat capacity. There's a problem sometimes with heat capacity when you are measuring first order phase transition, because the software of the system that I have is not trained to look at first order phase transition, because you basically send a heat pulse and you monitor the evolution of the temperature of the sample with time and do some kind of a fitting. But if there is a phase or first order phase transition, then the temperature doesn't change for a while. And then the fitting get messed up. But no, I went through several different temperatures around that, and we couldn't see a sign of first order phase transition. It's very elusive. And it is the sample, because these are single crystals. We can't detect any impurities. It could be a coincidence of some spin realignment that is such a way that the energy cost is zero. Like you lose entropy one way, you gain entropy another way with the spin realignment, and you don't see the change in heat capacity. But to your question about superconductivity, this is not a superconducting system. Incidentally, I'm collaborating with some folks from the University of São Paulo in Lorena, state of São Paulo.
Yes, there is a superconducting group, yeah.
Yeah. It's a group with Jefferson Machado. If you start with zirconium tellurium 2, it's not superconducting. But if you dope it a little bit with almost anything in the periodic table, it becomes superconducting. But we don't see any signal of the superconductivity in the heat capacity. So, the reviewers are skeptical about it. We are skeptical about it. We're trying to understand what it is.
Thanks. Just another question on the high temperature superconductors. So you showed that I think you are working on high temperature superconductors, or you are interested, and you have seen that for the charge density wave, the pressure increases the resistance, right? It destroys this charge density wave. True?
Yeah.
Yes.
Well, in that particular case.
Yes, but for example, in high temperature superconductors, at least some groups around the world are trying to explain the pseudo gap with charge density waves. So can you tell me what should I expect? I know what happens if I apply pressure to superconductivity, but what should I expect from pseudo gap if it is formed from charge density wave? Do you have an idea?
Yeah. To be honest with you, I don't. Okay. It took me a long time to understand the issue of this gap starting so much above TC. Okay. Yes. But finally, I forget what it was, some heat capacity experiments that convinced me that, that gap starts above TC. but I'm not working on it. And frankly, I don't understand. One problem with these materials, with the high TC superconductors, um, is that they are very hard. And typically, the pressure effect or the compression of the lattice is sort of inversely proportional to the hardness. And these are very, very hard ceramics. So with the pressure cells that I have, there's very little I can do. I do have some diamond anvil, but those are so difficult. They require so much. We only have a master's program here on my campus, and when you see people who work with this diamond anvil cells, it takes years of experience to set up these experiments. Everything has to be done in a microscope and all. So honestly, I haven't followed that pseudo gap issue very closely. So I don't know. It would be interesting to know how the
because it could be even a test.
Yeah.
Because if we know how charge density waves behaves with pressure, and we see pseudo gap behavior with pressure, maybe it can be an experimental proof of what we should be expecting to describe the pseudo gap, right?
Yeah. Well, it looks like the whole very high pressure community now is working on this hydrogen compounds, because only now the technology is up to that level. But still, there are only 3 groups around the world that can do this kind of work. And the predictions of metallic hydrogen came out, I think, in the 60s, right? That metallic hydrogen would be superconducting at room temperature. And now these guys are in hog's heaven.
That could be an excellent thing to happen.
Yeah.
Okay. Thank you, Dr. Milton.
Oh, by the way, there are some skeptics about this high pressure work with room temperature superconductivity. Okay. I'm not close enough to their thinking. This is a very theoretical thinking. I don't know if they are skeptical of their physics, which I understand. These guys are experimentalists like me, don't know any physics, or if they are skeptic about their experiments. There's one particular group at UC San Diego. Jorge Hirsch is the main scientist, and he's very critical. But from my experimental point of view, when you see they show the resistivity transition, okay, there are problems with resistivity transition, but they do show AC susceptibility, and you see the transitions there, which is a proof that it's a volume effect. When they show the resistivity data and they apply field, they drive those transitions to lower temperatures, and they fit the WHH or they fit the critical field models. So I'm more accepting of their results than some of the critics.
Thank you. It was nice hearing you.
Any more questions? Tem alguma pergunta, dúvida? Yuri Miller, você quer falar alguma coisa? Okay, so if you don't have any question, let's thanks once more, Professor Milton. Professor, it's very nice talk. Listen to
Hey,
you.
thank you very much. Very nice to meet you all.
Yeah, and virtual medium is a bit complicated one, but who knows, in some time future, we will see you in Brazil.
Okay.
Hope to see you.
Okay,
Thank you.
Bye-bye.
Muito obrigado aí, professor.
Obrigado. Tchau.
Okay. Ciao, ciao.
Tchau.